We're in Rhode Island, in Roger Williams Park, looking for waterfowl like this flock of Canada geese. Canada geese spend summers in the far northern part of North America, and there's a concern that while they were up there feeding, they also mingled with birds from Asia. And we want to take samples, send off to the lab to make sure that as they migrate south for the winter, that they don't spread avian influenza into the United States.
As we look at Southeast Asia and watch the progression of the avian flu, it's important to realize, first of all, that the avian flu virus as it exists now is really a problem primarily in birds. There have been massive die-offs of birds throughout Southeast Asia, even extending over into the Middle East and in Africa. But what happens is that when humans come into close contact with the birds who are infecting, people can get infected and they can die. And in fact, there's a very high mortality rate with avian flu, probably about 50% mortality rate. But what has saved us from a pandemic so far is that that virus doesn't transmit efficiently from person to person.
Humans have probably had influenza viruses at least for several thousand years. There are things going back to the Greek medical literature in ancient Greece that look like influenza virus outbreaks, although of course it's hard to know. Once influenza viruses get into people, they circulate on an annual basis, and they change a little bit so that they can reinfect people every couple of years. So the virus is trying to evolve to escape the immunity. People are trying to make appropriate immunity to these viruses, and so it's this kind of arms race that occurs. But it's influenza viruses that have the ability to go from one species to another that can cause a lot of trouble. And it's these viruses, because no one has immunity to them, during the first couple of years in which they circulate, tend to cause the most illness and death. In my laboratory, we're interested in understanding how it is that influenza viruses can move around between species and then how it is that they can cause disease. And we're very interested in studying what happened back in 1918 because we think it may have real relevance to understand this process. The 1918 flu was the worst influenza pandemic on record, probably the worst infectious disease outbreak in human history. Right now, scholars estimate that at least 50 million people died around the world. And so in a period of less than 9 months, 50 million people died of influenza virus in 1918, 1919. So that's just a really remarkable, a stunning number. It's a number that you can't really comprehend. This is a section of lung that's from a victim of the 1918 flu, preserved in formaldehyde and then embedded in candle wax. And when we started the project to try to understand the 1918 flu, we needed to start with sections like this, and we then use molecular methods to screen for tiny fragments of the influenza virus genome. These are then run on sequencing gel to allow us to see these fragments. And in some cases, we've been able to sequence the entire genome of the virus of 1918 flu victims. And we've been able to determine that the 1918 flu was probably entirely a bird flu virus that then somehow adapted to humans.
When viruses jump into humans and begin to spread, they spread quickly. So one of our challenges has been, how do we adapt the vaccine technology that we use for seasonal flu to be prepared for a potential human pandemic? In the past, when we've made flu vaccines, we actually grow whole virus, and we then inactivate that virus. What we're talking about now is to take the real core of what you'd like to generate the vaccine response to. It's called the hemagglutinin. And we're looking at ways of purifying that protein alone so that it can be used as a vaccine. The advantage of doing that is that you could probably make these much more quickly, and you could ramp in production much faster than you can with the current vaccine, which has to be grown in eggs. So if you're going to make a vaccine for 50 million people, that's 50 million eggs. So it would allow us to make the vaccine more efficiently and present to the immune system the real core of what we want to generate the antibody response to.
I think it's always a continual battle to deal with infectious diseases. But I think that certainly we have the ability to understand viruses and other infectious diseases at a level that certainly has never existed before, and that gives us great hope that we can develop new therapies and new drugs.
We share one planet, and essentially anything we do to change the ecology of that planet has an impact on any other species. So we just live in a very interconnected world, and that's going to be part of our legacy of evolution into the future.